Welcome. Welcome to the first session after the inspiring keynote of Avi. We have a session today in the BPM Forum series. So these are 4 papers that we'll be discussing, 4 contributions in the area of prediction, a topic that in machine learning or ML is probably a very, very well-known topic with very clear evaluation metrics and relatively many techniques available to do and build prediction engines and to do predictions. But in process mining, you will find from the presentations today that prediction is a far more complicated topic. I would like to introduce to you the first speaker of today's session, Stefan Pauwels. So Stefan is here with us from Antwerp, and I would like to ask you to start the first presentation, Stefan.
Okay, thank you. So share my screen. So, do you see my slides now?
Yes, thank you very much.
Okay. So hello everybody, my name is Stefan Pauwels, and together with my promoter Ton Kalders, we designed model for predicting next events and suffixes using Bayesian networks. In this presentation, I will first give a little bit of background information on how predictions are done and what definitions we use, on how we can take history of a trace into account, and what Bayesian networks are and how we use them to predict. So first, we start with predictions. So first, of course, we need events and cases. As a standard definition we use as an event has a unique identifier as an associated activity out of a pool of possible activities. And an event can also have a tuple of extra attributes with extra information like resource or department associated with the activity. Furthermore, events are gathered together in a case as an ordered list, and a log file is just a set of all cases. But before we dive deeper in the paper itself, we will first briefly introduce the running example. In this case, we consider an event log with activities A, B, C, D, E, and F, with one extra attribute resource, which has the values 1, 2, and 3. As you can see, our event log consists of 3 cases, where case 1 and 3 are similar and case 2 shows different behavior. And you can always see that the resource associated with the certain activity. For predictions, we consider 2 different types. The first type is predicting only the next activity in a partially completed case. And the second type is predicting the entire suffix for a partially completed case, where we keep predicting until an end event indicated in the example with the black activity has been predicted or a fixed size has been reached. To predict the next activity, we calculate the probability for every possible activity given the partial trace that already happened. When given the partial trace with activities A, B, and C, we want to predict the activity which is most likely to follow. Therefore, we calculate all these probabilities and select the activity with the highest probability. One issue with this approach is that the size of the partial traces can change depending on which event you want to predict. Also, for very large traces, a potentially large amount of data has to be taken into account. Both of these issues have a negative impact on the ability to learn a general model for activity predictions. To cope with these problems, we use a sliding window technique. For every event, we only look a fixed amount of time steps back in time. We call this the K prefix of an event. Like when applying a K prefix to our example, we can see that we now only take activities B and C into account because we have chosen K equals 2. This makes sure that we can have the same dimension for our history throughout the entire log. In this case, we have size 2, and every time step has 2 attributes, the activity and the resource. Before we introduce the model itself, we first take a look at the basics of a Bayesian network. A Bayesian network describes conditional probabilities between different variables. In the example on the slide, we have a system with 3 variables: rain, indicating whether or not it's raining; sprinkler, are the sprinklers working; and grass wet, just the observation whether or not the grass is wet. It is clear that there exist dependencies between these variables, as these variables all influence each other. The Bayesian network helps us identify the exact dependencies between all these variables. A conditional probability is the probability of a certain event happening given that another event happened. For example, we can consider the probability that the sprinklers are working given that it rains. We say that the variable for rain is a parent of sprinkler as it directly influences the possible values and their associated probabilities for the variable sprinkler. A variable can also depend on multiple other variables, like grass wet depends both on sprinkler and rain, as the grass can be wet both because of the sprinkler systems working or it's raining. Using these dependencies between variables, we can create a very detailed model explaining the behavior of a set of variables. When we go back to our example, we can now generate all the K prefixes that we'll use to learn a Bayesian network from. We use a sliding window to create all the 2 prefixes. In our case, that first event has no history, therefore we introduce null events for both historical time steps. The second event only has 1 previous event, therefore only 1 of these null events is added. And from now on, every event has sufficient history, so we do not have to add these null events anymore. The adding of these null events is mostly described as padding in the literature. So when we encounter the last event, we can stop creating more prefixes, as extra prefixes would not add any new and interesting information. Important to note is that starting from 6 events from the event log, we end up with a set of 6 events together with their 2 prefixes. A Bayesian network itself has no knowledge about activities and extra attributes or even the time that we use. Therefore, we flatten our events. In our example, we uncouple the resources from the events and add it as different attributes to the log. In order so we can make tables where every attribute is for the Bayesian network algorithm, every attribute has the same weight, is the same. It has no knowledge about any other meanings. But we, of course, can add meaningful column names to the K prefix log. So in the end, we know exactly what was predicted or what was learned. We then end up with a new log, and this log is called the K prefix log. It contains out of 2 main parts, the current and the previous part. The current part contains all events present in the original log, and the previous part contains information about the previous events occurring before every current event. After creating all prefixes, we can create a table which contains all probabilities for all combinations of current and previous values that occurred in the dataset. The data on this slide depicts the probability for a combination of activity and resource given the previous values. As we want our model to be more flexible than only exactly being able to reproduce what already happened, we learn all dependencies between attributes from the previous time step to attributes in the current time step separately. Like, for example, we have a history with 2 activities and 2 resources and a current activity and resource we want to predict. So we put a restriction on the Bayesian network learning algorithm, indicating that it can only allow dependencies from an attribute in the previous time step to an attribute in the current time step. This makes sense as we only want to use historical information to predict next event. After running the algorithm, we might see displayed the result. In this case, both activity and the resource depend on the activity and resource from the previous time step. We just see that looking further back than 1 time step would not increase the amount of useful information present in this log file. Important to note, however, is that the user can inspect this learned model and is also able to manually change dependencies if needed, so he can remove dependencies or add dependencies between variables as needed. When we have learned the structure of the model, we can then learn all individual conditional probability tables. These tables contain the probability for every attribute individually, given the attributes on which it depends. Although activity and resource both depend on both activity and the resource from the previous time step, we can see that their conditional probability tables are different, indicating why we have 1 separate table for every attribute in the current time step. We can then use these tables to determine the probabilities for all possible activities, given activity C and resource 2 from the previous time step, as indicated on the slides. Of course, this is a very easy example. That's why all probabilities are 0 except for the correct activity. When using conditional probability tables, we can encounter different situations. First, the combination of previous values is completely known. In this situation, we can just look up the values in the table and get the probability attached to it. And secondly, the combination of previous values is not known. Then we have two different situations. One situation where all individual values are known, and one where some of the values are unknown. For the last two situations, we can marginalize over all possible values using the learned conditional probability tables. So our experiments consist of three parts. First, to look at the predicting performance of our model for both the next activity and suffix prediction. Our last experiment looks at the time needed to learn the model. We compare our methods with recent state-of-the-art neural network methods. We selected these methods as they contain both a variety of use techniques and are still very relevant. The data sets used are also selected by looking at the recent papers. So first, in table for next activity accuracy, we can see that our model performs fairly well and regularly also outperforms existing methods. For suffix, however, this table shows that our method is less suited. But an interesting thing to look at are the runtimes for the training of the models. And we see then there are a huge difference between our model, which actually only just use counts and probabilities in contrast to the neural network methods. Even when running the neural network methods on the GPU infrastructure, they are still much slower than our Bayesian network method. Mostly it's because of the sequential nature of LSTMs, for example. That's why you can see also the CNNs perform much better than LSTM methods. And then to conclude, in our paper, we introduced a new method for predicting activities based on Bayesian networks. The big advantage of this method is that it's fast training times and explainability of the model and the possibility for an expert to adjust the model. We compared our model also with state-of-the-art methods, which showed that we outperformed some of these methods on the data sets. We also showed that our model in its current form is not suited for predicting suffixes of a case. But because our learning of our model takes less significant time, our model is also be able to update while running, or you can easily learn a new model every day with new events arriving. So I'd like to thank you for your interest, and if you have any questions, please ask them.
All right, thank you, Steven, for your presentation. Now, for the attendees to ask questions, please use the Q&A or the raise hand option, and then we can give you the floor. I see no questions coming at the moment. So, Steven, you talked about explainability, and this nicely matches with the keynote we saw earlier today, where Avi basically said that in process mining, explainability relates to simplicity. The example you showed on the slides, and for good reasons, is a simple example, but how explainable are the more complex Bayesian networks learned on real-life examples?
We have done one big experiment on explainability using for the BPI Challenge 2018, where we used the same model for explaining drifts in a data set. And there it was very clear that you could see both by the dependencies learned as with the scores or the predictions, the probabilities that you get for different values. Then we could use these values to predict or indicate, which attributes contributed to a drift, for example.
Okay, thank you. There's a question from Rizzy Williams.
Yeah, so thank you for your presentation. I was wondering, at the end of the presentation, you mentioned that your model could be used also to make incremental learning and update the model on at runtime. I was wondering if you did any experiment on that, and if you can give us a sneak peek of the results, if you have any.
Yeah, I did use the updating in an experiment, and it did give very good results, like an improvement of 20% in accuracy when you test. Every time you tested one event, you just add it to your model. And we had a 20% increase in some of the data sets, especially the BPI challenge from 2015, because they do have some drift occurring because of departments switching, etc. And then we saw a huge increase. Unfortunately, we couldn't yet compare it with performance. If you would use the neural nets, for example, to update, we didn't have possibility for that. But there's also a kind of difficult and a different story for the neural nets, as you've got forgetting that can occur if you keep updating a neural network. But it's certainly something we are looking into for further research.
Thanks.
So we have one more question. So I'm going to give the floor to Freddie. So I'll push the unmute button. Freddie, would you like to ask your question? Does it work? No? Then perhaps let me just read the question to you, Stephen. So the question is, yeah?
Now I cannot hear the others, but can you hear me?
Yes.
Somehow my audio is gone. I see the microphone is working, but someone muted me. Okay, my question is, yeah, I cannot hear the answer. That's a bit pity. But is the model limited to one property per activity, and have it to be the same property? And if no, how many properties are supported? And do the properties all be the same for all activities?
So
yeah,
you can
no,
add...
I cannot hear, so it would be nice if someone would turn on my speaker again.
Can you hear us now?
I cannot hear.
Still not fixed. Should I just give an answer, or?
Yes, I think
still...
if you can answer the question, then Freddie can also.
Yeah, I'm here.
You're back.
Okay.
Yeah, somehow I get no sound, and I can hear you guys, so it would be nice.
So the model itself is not limited to a certain amount of properties for every activity. As a Bayesian network works on variables, you can add as many variables as you want. The only limitation is the computation power you have, because of course, the more attributes you include in learning the Bayesian network, it almost exponentially increases the number of possible dependencies between all these variables.
Yes, but that means also that the properties / variables need to be the same for each and every action, right? Because from my observation in the real world, for every action, it's a different set of variables.
Yeah, indeed. So you need at least one shared set of attributes, but one extension you can do is like add non-values. And we also included in the learning algorithm that non-values are not considered real values for considering the dependencies between attributes. So they're just ignored.
Thank you, Stephen. In the interest of time, I think we need to move on to the next presentation. So once again, thank you, Stephen, and I would kindly ask Vincenzo to start sharing his screen. So Vincenzo will be presenting the paper on prediction and computer vision. And this is the one paper where there is actually already a comment on the WOVA that somebody's looking forward to this paper. So please go ahead, Vincenzo.
Can you see the slides?
Yes.
Okay. Good morning, everyone. I'm Vincenzo Pasqua di Biceglia, PhD student at the Department of Computer Science at the University of Bari. I present you our work, Predicting Process Mining meets Computer Vision. Why predicting process mining? Thanks to the availability of a large amount of data produced by large company related to the production process, is possible to monitoring the process instance. And for this reason, machine learning coupled with predicting process mining techniques is possible to make a useful solution in order to increase the quality and support the decision-making process. In the literature, there are several tasks related to the predicting process mining. In particular, the predicting process mining research involves in several tasks, such as next activity prediction or completion cycle time until a trace is completed, or outcome prediction. In this work, we are focused on the next activity prediction task. In the literature, there are several works based on next activity prediction tasks. First of all, we have the first approach based on the Petri nets and transition system. This type of approach are based on process discovery algorithm in order to understand of the trace are performed. In this case, this type of approach are based on the formal language such as Petri nets. The second type of approach are based on machine learning algorithm in order to learn a predictive model for the next activity prediction. And the last type of approach are based on deep learning algorithm. In this case, the representation of the traces are based on a sequences representation. And for this reason, we have LSATM architecture or Con1D architecture, for example. The proposed approach is called Premiere. Premiere is a novel deep learning approach that combines computer vision and predicting process mining technique. Premiere pipeline is composed by 4 phases. The first phase is the feature extraction, followed by RGB encoding. The third phase is the next activity predicting model, and final prediction of the next activity. First phase is the feature extraction. Starting from historical event log, it's possible to extract a feature vector useful for prediction. In this case, in this work, we have adopted a feature engineering schema aggregate feature engineering. And in this case, we choose three views from the historical event log: activity and control flow perspective, resource perspective, and time perspective. The second phase is RGB encoding. This is a crucial phase because the basic idea of this phase is to map each value of feature vector to a single pixel of an RGB image. First of all, we apply a min-max normalization on feature vector in order to assign the same weight of each value of feature vector. In this case, it's possible to apply the following formula for each value of feature vector in order to obtain a 24-bit value. In this case, it's possible to split this value into 3 8-bit values in order to obtain an RGB channels. This process is applied to each value of feature vector in order to obtain an image, an RGB image. This is an example of an RGB images extracting from consecutive prefix trace on one trace stored in reset phase log. This is the neural network architecture adopted in this work. In particular, in this case, we apply inception module. The basic idea of this architecture is composed by 3 parallel convolutional layers, followed by a max pooling layer. The results of a concatenation of this layer is forwarded to a dense layer and then passed to flattened layer in order to obtain a feature vector useful for classification. This is the experimental setting adopted in this work. We performed the threefold cross-validation for evaluate our solution, and the three-partisan estimator was adopted for hyperparameter estimation of neural network architecture. In order to evaluate the performance of our solution, we have adopted the following metrics: accuracy, precision, recall, and F1 score. These are the dataset adopted in this work. In details, we have adopted the BPI 12 complete, BPI 12W complete, recept phase, and BPI 13 problems. In this slide, we can see the results of Premiere and their competitor. In details, we choose 5 state-of-art competitors, and in this case, we can see that in general, Premiere overcome the other competitor, exception for precision in recept phase, and the F1 score in BPI 12 complete. The other competitor are based on deep learning architecture. In particular, Camargo et al. Adopted an LSTM architecture with an embedded representation of activity plus a role of resources. Di Mauro et al. Adopted a ConWAD architecture with an embedded representation of activity plus timestamp. Tax et al. Adopted a one-hot encoding representation with an LSTM architecture. Everman et al. Adopted a recurrent neural network with an embedded representation of activity plus life cycle. And Pasqua Di Vicelli et al. Adopted a convolutional neural network with a 2D representation of running trees. In this case, Premiere is the first approach that based on RGB images of trees. As future work, we have planned to improving the empirical investigation by considering new event logs, exploring different process predictive tasks, such as outcome prediction, exploring the standard 2D CNN architecture, for example, ResNet, investigating the performance of 3D CNN architecture based on video trace representation, and extending the pipeline to deal with the streaming scenario by accounting for concept drift. These are our contacts, and thank for your attention.
All right, thank you, Vincenzo. Again, if there are questions, please use the raise hand button or post them in the chat. Nobody. So Vincenzo, can I ask you, one of the issues in prediction is that in processes it's very difficult to avoid clairvoyant predictors. So when you prepare your data, for example, you're predicting outcomes or other features, that in your training data you encode things that actually are not available at the point in time you do the predictions in your test data. So think of the outcome of a process, of a case in your training data that is available later in the year, let's say in March, and then you're doing predictions. So you build a model that contains this case, and then you're doing predictions at the moment there is an event that actually happens in January, and you predict based on the model you trained for results that were only available in March. So how would you deal with this like bias in your prediction model?
In this case, we are fix the threefold cross-validation. because in the literature there are no standard for this reason, because different work adopted a different experimental setting, and for this reason we are choose this experimental setting in order to avoid an unfair comparison. In this case, we have launched the other competitor with the same setting in order to obtain a fair comparison. In the future work, we adopted this a kind of split in order to considering the time perspective.
Good, thank you. Other questions?
No more questions that I can see, so I think we can move on to the next presenter.
All right, thank you, Vincenzo. Thanks, Mo, for helping keeping track of all the chats. So the next presenter is Sven Weinzel.
Hello. Hi.
He's joining us from Nuremberg, and you will be talking about process monitoring. So you go one step beyond prediction. You're actually going to recommend what you should do next, rather than just predicting what happens next. And we can see your screen, but we're still looking at the not in presentation mode yet.
Yeah. Yeah. So now we should be in the presentation mode. Great. Hi, my name is Sven Weinzel. I'm a PhD student at the Friedrich-Alexander University in Erlangen, Nuremberg, Germany. Today, I have the pleasure to present the paper Prescriptive Business Process Monitoring for Recommending Next Best Actions. The paper was co-authored by the authors Sebastian Dunzer, Sandra Zilker, Martin Matzner, also from the Friedrich-Alexander University in Erlangen, Nuremberg. Regarding the agenda, first of all, I start with the motivation, followed by contribution, the artifact. That means the concrete technique that we present here, the evaluation, and finally conclusion and future work. In the last years, researchers have proposed many predictive business process monitoring techniques. These techniques try to predict future process behavior. For example, the next most likely activities, in order to improve operational business processes. However, organizations measure their performance by KPIs, and prescriptive business process monitoring goes one step ahead. It is a set of techniques trying to assess the prediction regarding the impact on the process performance to undesired process activities by raising alarms or recommending actions. Against this background, we propose a novel technique for recommending next best actions. The technique that they present consists of three central elements. First of all, the next activity prediction, or rather the prediction task. For that, we use deep neural networks or a network architecture proposed previously by the literature. Second, the KPI optimization. For that, we used nearest neighbor-based candidate selection. More details will be presented on the next slides. And the third element is conformance. For that, we use a state-based simulation. To get an intuition about the idea of our technique, I want to start with a simple example. We have here 5 different activities on the left side, A, B, C, D, E. 3 different configurations, A, B, and C. The configuration A, we have the scenario of the prediction of the next most likely activity. In this case, in this case, the first activity E, B, and then D, E. The first 2 activities take each day per activity. Then the next most likely activity is predicted. It is D in this case, the resubmit activity. It takes 3 days, and last but not least, an activity E takes 2 days, and some will come to 7 days. The second configuration B is a preliminary prototype of this technique that we present in this paper. We presented at the VE conference 2020 in Germany, and we start with in this configuration, we have AB in 1 day, and then last but not least, we recommend activity E. It takes 2 days, it comes to 4 days. But the problem in this prototype was that the process is not conformant. So in the last setting, in the last setting, we have A, B, and D, C. So we recommend C. And after C, we have D, E, and some we come to 6 days. The difference here is that it is conformant to the process because the step revised manuscript is relevant, followed by, or revised manuscript is relevant, then submit, and finally get accepted. So we have here, to sum up, we can save with configuration free or C 1 day. So PR, that's the abbreviation of it. PR BPM recommends conformant next best actions that optimize one KPI in process instances. Further, I would like to go on with the artifact. It consists of an offline and online component. The offline component is for training the model. For training the models, first we pre-process the event log for process prediction. For that, we add termination event to the end of a process instance, not encode all activities. We crop out the prefixes of the process instances, and finally we transform it in tensors and in a matrix so that a neural network can deal with it. In the next step, what is with the presentation? So we have some technical issues here. Sorry. So this, okay. The second step is to learn the predictive model. For that, we use the model of Tax et al. This model uses an LSTM with a shared layer and predicts not only the next activity, but also can also the time. We consider the time as an KPI value. In the third step, we pre-process the event log for candidate selection. For that, the ordinal encode all activities, crop the prefixes, the suffixes out of a process instance, and transform the suffixes into a matrix. In the last step, we learn a candidate selection model. That means a second model. For that, we use an nearest neighbor-based algorithm. It takes as input the suffixes, and it has the task to retrieve the k suffixes nearest to the prefix predicted for a given prefix. After the offline component, we go on with the online component. It starts with the pre-processing of a process instance. Here again, we will not encode all activities and perform a transformation of the prefixes of a prefix into the tensor, because we have here process instance are running trace. Then we have we predict the suffix. We apply the model that we learned previously in the offline component repeatedly to get the complete suffix. We sum up the KPI values over the activities of a complete process instance. That means the prefix plus the predicted suffix. And we use a condition. If the total KPI value exceeds a threshold T, the procedure for recommending next best actions begins. And T can be determined by domain experts or can be calculated from an event log, for example. In the next step, we'll find candidate step. We apply the second model, the candidate selection model, to retrieve a set of suffix alternatives with a meaningful control flow. In the select best candidate step, suffixes are sorted by the KPI value. The first suffix is the best one with regards to the KPI value. Additionally, we use a simulation model that checks the resulting instance. If the prefix does not comply with a process model, the simulation aborts the suffix selection for the prefix. Otherwise, the case selected suffixes are checked. If a condition holds that all suffix candidates infringe the simulation, the predicted next activity is assumed as the next best action candidate. In the last step, we have an update. In this update, the first activity from the selected suffix is concatenated to the prefix. To complete the complete procedure, as I have presented it, is repeated until the termination event is reached. Further, regarding the evaluation, we used two different event logs, the helpdesk event log and an sample from the BPI 2019 event log. And for the with respect to the process simulation, we constructed one process model for each event log. In the procedure, the evaluation procedure, we split each event log into a 2/3 and 1/3 training and test set with random sampling. As baseline, we used the approach of Tax et al. From 2017. And as KPI, the throughput time, the threshold was calculated from the log. It is the average throughput time of a process instance in an event log. And finally, the metrics are on the one hand, the fulfillment of the KPI in time, and on the other hand, the distance from ground truth. That means the average Demarou-Levenstein distance. The results for the help desk shows us that our next best actions are more in time than the next activity predictions. Or we also saw that the higher the K, the lower the distance, the K of a suffix selection, the candidate selection. Of our next best actions from the actual process instances. And we can also see that up to a prefix size of 4, the distance of next best actions is lower compared to the next activity predictions. For the event log BPI 2019, the most prefixes with a size greater than 8, we can say that the next best actions are more in time than the next activity predictions. With the increasing K, the in time values of the next best actions vary less from prefix size 2 to 12. And in contrast to the next activity prediction, we can say the distance, or we could observe that the distance of the next best actions is lower for prefixes with a size greater 3 and lower 15. So that brings us to the conclusion and future work. Conclusion: next best action can be more beneficial for process stakeholders. Our technique can outperform the baseline regarding KPI fulfillment and the distance from ground truth. There are a lot of directions for future research. Here are listed only 3 of them. First, an adoption of existing loss function to directly incorporate KPI information or the information of KPIs. That means if you look at a neural network, we have a loss function is an intrinsic or an element of a learning procedure, and it is if someone engineers the loss function and tries to incorporate the KPI information, we could better, or we can maybe to a certain degree ensure or control the learning in direction to the KPI, or more in direction to the KPI. Second, someone can use a more advanced multitasking DNN architecture. That means, or that is very interesting in terms of considering more than one KPI at a time. And finally, the design of a prescriptive business process monitoring technique that can deal with, recommend with activities that have not been observed in the event log data. I think that is a very interesting thing because, predictive business process monitoring strongly relies on historical event log data, the event log. Our prescriptive business process monitoring tries to transform the next most likely activity prediction into something like an action. And how can such a technique can deal with activities that have not been observed in the event log data? I think that is also an interesting question that can be answered. Thank you for your attention.
Right, Sven, thank you. And again, for the audience, if there are any questions, please raise your hand or type them in the chat or in the Q&A. There is a hand going up. Several, actually.
There are two.
Mahmoud, can I ask you to?
Okay. So, what is the
We unmute.
Yeah, so Mahmoud Shush, you should be able to unmute yourself and ask your question. No response. Carl Correa.
Hello.
Hi.
Can you hear me?
Yes, please.
Okay. So thanks for this very interesting talk. I think I'm going to have to look into it. So my question was a bit geared towards compliance. So maybe this was in the candidate selection. So my question is, your recommendations for best actions, I think, are geared towards saving time. But I don't know if a shorter time is always plausible, because maybe the recommendation is faster, but it's simply not allowed. So my question is, how do you incorporate compliance in the sense that your recommendations are actually allowed and plausible in a real life sense?
Yeah, a very, very good question. Thank you for this question. Yeah, that was the biggest problem at our preliminary prototype, that we recommend something that is optimized but not conform to something to the semantic of a process or semantics of a process. And so we tried to bring both worlds together. Something in this case we used declarative modeling and a model, and on the one hand, on the other hand, yeah, we have the output of a predictor that is in probability distribution and so on. And so we tried to ensure the correctness. I'm sure that are better ways to do that, or maybe other ways to do that. And there's a lot of potential to improve that at this point. And I see it as a further stream or direction for research.
Mm-hmm. Okay, thank you very much.
All right, other questions? Mahmoud, you are
back.
Yeah, there you
go. Do you
hear
me?
Yes.
Yeah, thank you. Thank you for your presentation. I have two questions. The first one, can we recommend the best next action to get a specific desired outcome? So it's kind of a twofold approach. First thing, we need to predict the best next action. And also we need to consider the desired outcome. This is the first one. The second question, did you consider the best time that you raise your recommendations, or just you get it out?
Okay. I start with a simpler one. The second question, I think it depends on the event log. The time where you can give something like a best action. As we observed in during our experiments that it's also for predictive, also for prescriptive. It depends strongly on the structure of the event log, and most of the researchers, or it seems like to me, that they're more interested in the machine learning stuff, but not so interested in the structure of yeah. And I think that is also very, very important, because if you look in the event log and have a process model and see what happens, or it gives you more insights if it is realistic to get I say good prediction. Yeah. So the time depends on something like decision points. If you have a process model, you see the different decision points, and then you see, okay, you have maybe a process that is something like workflow, and then we have decisions. So it's later in time. So if you have other process that, so we have here a difference. Yeah. That is the one point, and the answer is it depends on the event log. And the first question was, I think it is a bit more if it is at all possible to give something like a next best action. Of sure, best is a difficult term. What means best? We define best in this paper as or with regard to the concrete KPI value or KPI that we consider. It is very difficult if you have someone say, we would like to optimize 2 KPIs, for example. We say, okay, it should be cost efficient and time efficient, maybe, for example, and then we have some problems because maybe we can optimize the one, but the other one is not optimized and even getting worse. Yeah, and that is the problem. And we tried with this paper to go the first step in this direction, prescriptive business process monitoring with for recommending next best actions. But yeah, we see it as a first step in this direction.
Thank you.
All right, thank you. We're now moving to the last speaker of this session. The paper has 2 titles. So I'm going to leave it up to the authors and the presenter to actually tell me the exact paper. In the program, the paper is listed as Make Your Flaw Your Strength. But in the proceedings, the paper is shown as Explainability in Predictive Process Monitoring, when understanding helps improving. William Zrizi is here to present it, so I'll give the floor to you.
Thank you. So the title is actually Explainability. Sorry, let me share the screen. Can you see my screen?
Yes.
Okay. So the title is actually Explainability in Predictive Process Monitoring. When understanding helps improving. So hi everyone, my name is William Zrizi, and this is a joint work between the Free University of Bolzano and the Fondazione Bruno Kessler. So in machine learning based predictive process monitoring, we feed sets of past historical traces and a prediction problem to a machine learning technique. The machine learning techniques returns as a predictive model that we later use at runtime on the current ongoing trace to make predictions. In this case, the prediction, as you can see, is false. And the problem in this sort of approaches is that sometimes they can make errors and therefore give us wrong predictions. And as you can see in the sketch of our little doctor here, wrong prediction can degenerate and cause catastrophic situations. What we want to do in this work is understand what makes the predictive model return wrong predictions, and then act upon this knowledge, leveraging the retrieved information to enhance the predictive model. To do this, we will use 2 ingredients. The first one is the confusion matrix. So going back to the binary classifier in our example, a binary classifier can predict two possible labels, true or false. And in turn, this prediction could be correct or wrong based on the actual future of the execution trace. This leads us to 4 possible outcomes that you can see here. Each element inside the quadrants of our confusion matrix corresponds to one trace of our testing set, for which we want to make predictions. So the second ingredient instead is the post hoc explainer. So going back to the binary classifier of our example, even if the binary classifier is considered a very simple model, it is rather difficult to debug it, even if it's white box by construction. Different approaches to analyze the behavior of a trained model are available in literature, and we decided to exploit post hoc explainers. A post hoc explainer for each trace is capable of retrieving the contribution of each feature value pair towards a prediction. The weight of each feature value pairs allows us to establish its impact toward a certain prediction. So as you can see down here in this example, we have a simple trace with simple features. And in this particular case, go home at 5:02 p.m. is considered by the post hoc explanation very important to give a false prediction. The same for park car, whereas open door is slightly less important and is trying to make the predictor give us truest prediction. So how do we put together these two ingredients? Our recipe is the following. So we take the test set and we compute the explanation for each of the traces of our test set. Then we take the confusion matrix and we substitute the explanation to the traces. In this way, we end up with an enriched confusion matrix that is full of information. The problem is that there is way too much information in this confusion matrix. Therefore, we filter it. And as you can see here, in each quadrant, for each trace, we filter out the feature value pairs with a weight lower than a given threshold. As you can see here, you will notice that some of the features are disappeared. After that, we group together the similar patterns inside each quadrant using association rule mining algorithms. So what we end up with is what we call frequent explanation item sets. A frequent explanation item set, you can think of it as an explanation or a characterization of the traces populating each and every quadrant of our confusion matrix. So as you might have noticed, in some cases it happens that some frequent explanation item sets appear both in correct quadrants and in a wrong quadrants. So since we are trying to act upon the wrong prediction and try to enhance our model, we need to remove these characterizations that are good, and therefore we end up with the bad frequent explanation item set. You can think of this particular frequent explanation item set as an item set that is trying to tell us that when an activity that is, for instance, open door, is directly followed by another activity that is enter flat, for instance, by a very short amount of time, this is where our example is making wrong predictions. So right now, we identified the correlations and we characterized the motivation behind the errors of our model. Now we need to lower down the impact of this particular bad frequent explanation item sets. And to do that, we'll take a two-step approach. First of all, we will identify them in the training set. And after we identify them, we will shuffle them. So what we are actually doing is try to break these random correlations that are available inside our training set. And then after we broke these correlations, we retrain our model and then we evaluate it. So for what regards the evaluation of our approach, we formulated two different research questions. The first research question is trying to check whether the frequent explanation item sets can be used to characterize the quadrants of the confusion matrix. And the second one is trying to understand if shuffling the bad frequent explanation item sets is a good solution to improve the accuracy of the predictive model. So for what regards the first research question, that is, can we discover appropriate frequent explanation item sets? We synthetically built a model in a way that we know when it provides wrong predictions. And then we qualitatively verified that the frequent explanation item sets model correctly the wrong prediction. And what we have found is that we are capable of discovering good frequent explanation item sets, and therefore we can positively answer this research question. So for what regards the second research question, that is the randomization a good option to enhance the quality of our predictive model? We tested our approach on both synthetic data and real-life data with different encodings and different labelings. And as you can see here, we have 3 different settings. The first setting is the baseline, that is the model that we use to compute the frequent explanation item sets. Then we have the retraining one, that is using the shuffle and retrain procedure on top of the most occurring frequent explanation item sets. Whereas the retraining 2 is using only the second most occurring frequent explanation item sets. The results are pretty satisfying, as you can see. The retraining 1 is showing very good results and is showing that it is capable of enhancing the predictive model. Therefore, we are positively answering also to this research question. And concluding my presentation, in this paper, we have shown an early work of a way to provide feedback to the model and enhance the predictive model. In this work, we shown that we are capable of retrieving frequent explanation item set that can be used to explain the errors of the model. The randomization of the found frequent explanation item set enhances the quality of the model after retrain. And in the future, we will investigate how understandable or usable are the frequent explanation item sets to the final user on their own, let's say. And we will try to extend this technique on multi-class classifier and experiment with other predictive models. So thank you for your attention. My presentation is finished.
Thank you. Right, so once again, I would like to open the floor to questions.
There's one person who would like to ask 2 questions. So, Kata, are you able to talk now?
Maybe we should just read it out.
Do you want to unmute? I can't.
No? So shall we just read them then, Mo? So the first question is, how could you overcome the instability in the results of Lime?
Okay, so we built our approach in order to be very modular, and we are aware of the fact that Lime is not the best model the best approach in providing explanations. In fact, we are planning to substitute it either with SHAP or some of the approaches that we have seen yesterday at the workshops. In order to overcome the instability, actually, when we are filtering and when we are mining the frequent explanation item sets, since we are using multiple traces from data set, we are capable of, let's say, filtering out the instability and therefore isn't also the, let's say, bad behaviors of Lime.
All right, thank you. So there is a second question, the follow-up. So by randomizing the values of features that cause the classifier to yield wrong predictions, won't that be forcing the classifier to overfit on the features that actually cause the right predictions?
So that is a problem that concerned us quite a bit. In fact, we are using 3 different sets, and we are randomizing only one time for each evaluation, let's say. So the retraining one is retraining only once, and we are forcing it to act only on one frequent explanation item set per time, so that we are sure that we are not we are ensured by this, let's say, little thinking that we are not overfitting on wrong or good predictions.
All right, thank you. Then another question came in from Renuka Sindgata. Can I ask you to try to ask the question yourself?
Yeah, sure. Thank you very much. I had this question about would this approach also consider when a model uses wrong explanations but makes the right predictions? Because right now it looked like we're looking at false positives and false negatives of the confusion matrix. Would there be a scenario when even the true positives and true negatives are using wrong features?
We are not acting on top of the explanation that we retrieve from the correct predictions, but yeah, that might be a problem. In particular, if we use Lime as a post hoc explanator, there is a number of papers in the literature that show that post hoc explanators are not actually the best in modeling what the predictive model is actually trying to do on top of the trace. So I'm not sure what we could do on top of the correct prediction right now, but I'm glad to look into it in the future.
Sure, thank you.
Thank you.
All right, thank you. And thank you to all the presenters. Are there any further questions? There's still some time left. But if not, then thank you again. Oh, there's one hand coming up. Let me see. Mathilde, please go ahead.
Hi, can you hear me?
Yes.
Yep.
I feel like that your work can be done on other data sets, not only process instances. So have you been inspired by a work that did it on other field, in other field, or did you invent this entire process, and or have you been inspired? I don't know.
Sorry.
My question is, so your work is to explain the model, to improve the model, the prediction model, right?
Yep.
And I wonder if this work has been done in other fields, in data mining, in language, natural.
We have looked into it, but we did not find much in this in this behalf. The inspiration of this work comes from the feedback loop that you use in engineering when you try to model the working of an electric motor. But it was very randomic as an inspiration, and there is no, let's say, straight connection between the two approaches. So no, I'm not aware of any other, right now, I'm not aware of any other.
Okay, good.
All right. Thank you for the last minute question. I think this is it. Thank all the speakers today for their contribution. I recommend that you also look at the papers and download them from the website. And I think with that, it's about time for lunch. Thank you, Mo, for helping me sort out the Zoom mess, and Sergio for setting this up, let's say 15 minutes before you all joined. So thank you all, and see you again later this week.
Thanks.
Bye, everyone. Thank you. Do we stop the recording, Barbara?
Yeah, I was thinking about that. I expected Sergio to do that, but yep, there he is again.
Yes, hi guys. I was waiting for the people to leave, but yes, I think we can leave now. I will stop the recording.
Right.
Thank you for everything. Great session. Thank you.
Thank you for all the help in setting it up.
Bye.
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 Bye, thank you.
Bye, thank you all.